Welcome back. I hope you had the chance to watch my previous video where I explained how to derive the equations of motion. If you haven't, I recommend watching it first. The link is given above so you can understand the derivation process. In this video, we'll go through a few examples to explore the motion of an object under gravity and see how these equations can be applied in problem solving. Let's start with a simple example and later move on to more challenging ones. In our first example, let's consider a ball thrown vertically upwards with an initial velocity of 20 meters per second. We need to determine the maximum height it reaches and the time it takes to reach its highest point. To solve this, we'll use the equations of motion under gravity, keeping in mind that at the highest point, the velocity becomes zero. Now, which equation should we use? Since we're looking for the maximum height, we need an equation that includes displacement. The obvious choice is this motion equation. Using this equation, we can directly solve for the maximum displacement by substituting the given initial velocity and setting the final velocity to zero, since the object momentarily comes to rest at the highest point. However, instead of using this equation right away, let me first approach it in a different way, using this equation. I'll show you why this alternative method is useful and how it gives us deeper insight into the problem. Remembering only this equation is more than enough to solve almost all problems related to motion under gravity. This single equation allows us to determine velocity, displacement, and acceleration without needing to memorize multiple formulas. By understanding how to apply it correctly, we can solve any problem involving freefall, projectile motion, or vertical motion under gravity with ease. In this equation, S of t represents the displacement of the ball at any given time t, measured in the upward direction, which we consider positive. Now, what is S sub 0? This represents the initial height of the ball. In this example, the initial height is 0. U is the initial velocity, which is 20 meters per second, and A is the gravitational acceleration, which we take as negative 9.8 meters per second squared. Since we are measuring all displacements and velocities upwards as positive, we consider the gravitational acceleration as negative because it acts in the downward direction. Before we proceed, let's simplify the expression. All right, our goal is to calculate the maximum displacement reached during the object's upward motion. I'll demonstrate a method to determine both the displacement and the corresponding time in a single expression. To achieve this, we need to rewrite the given expression as a difference of squares. Let's go through this step by step. First, we'll introduce a squared bracket, ensuring the coefficient of t squared is factored out. Then, we'll carefully include the second term inside the bracket so that when expanded, it yields the 20 times t term. However, when we expand the squared bracket, an additional term appears. That wasn't part of the original equation. To address this, we need to subtract the extra term to maintain the equation's balance. Why did we use this method? In motion under gravity, displacement as a function of time is represented by a quadratic equation. The maximum displacement, achieved at the highest point of the trajectory, corresponds to the vertex of the parabola. By completing the square, we can directly calculate both the maximum displacement and the corresponding time without relying on differentiation or other approaches. The maximum displacement occurs when the component on the right side of the equation equals 0. Specifically, at time equals 2.04 seconds, the displacement reaches its peak value of 20.41 meters. I hope this approach offers you a fresh perspective, moving beyond a rigid reliance on standard motion equations. It not only deepens your understanding of the underlying concepts, but also strengthens your problem-solving skills for tackling problems of this nature. Let's move on to the next question. In this problem, a ball is thrown upward with an initial velocity of 10 meters per second from a height of 5 meters. We need to determine three key details. First, the maximum height the ball will reach. Second, the time it takes to reach this maximum height. And third, the total time taken for the ball to fall back to the ground. We'll begin with the equation for the displacement of the ball, which is given as follows. The ball starts with an initial displacement of 5 meters, so S sub 0 is 5. Next, we can substitute the initial velocity of the ball, which is 10 meters per second. This value is positive because it aligns with the direction of the displacement. We know that gravitational acceleration, 9.8 meters per second squared, acts in the direction opposite to the ball's motion, so we take it as negative. Finally, after simplifying, we arrive at this equation for the displacement of the ball in the vertical direction. To better understand the motion, let's sketch the displacement time graph of the ball. Since displacement follows a quadratic equation in time, the graph takes the shape of a parabola, visually representing the ball's rise and fall. The highest point of the curve corresponds to the maximum height reached. Now, let's examine the velocity time graph. By differentiating the displacement equation, we obtain the velocity expression. Here, v of t represents the velocity of the ball at any given time t. The derivative of the displacement expression gives us the well-known equation of motion. By substituting the initial velocity of 10 meters per second and the gravitational acceleration of 9.8 meters per second squared, we can determine the velocity of the ball at any given time. Initially, the ball has an upward velocity of 10 meters per second, which gradually decreases to 0 at the peak, before becoming negative as the ball falls. This explains why the velocity time graph extends into both the positive and negative regions, positive for the ascent and negative for the descent. A key observation is that at the peak of the displacement time graph, the velocity is 0. Consequently, in the velocity time graph, the function crosses the time axis, indicating this moment of 0 velocity. This point marks the transition from upward to downward motion. Now, what about the gradient of the velocity time graph? By differentiating the velocity equation, we obtain a constant negative value, the gravitational acceleration. This tells us that the slope of the velocity time graph represents gravity, which always acts downward. Since we've defined the upward direction as positive, the gradient is negative. These graphs describe vertical motion under gravity. Later, when we explore projectile motion, we'll refer back to these concepts to analyze vertical displacement and velocity in more complex scenarios. With that detailed explanation, let's return to the question: finding the maximum displacement, the time taken to reach this point, and the total travel time of the ball. We have two approaches to solve this problem. We can either use the displacement time graph to determine both the time and maximum height, or use the velocity equation to find the time to reach the highest point and then substitute it into the displacement equation to calculate the maximum height. Let's start by using the displacement equation to find both the time and maximum height. To do this, we need to rewrite the expression as follows. If you recall from the previous example, the maximum displacement is obtained when the term inside the bracket equals 0. The term inside the bracket becomes 0 at 1.02 seconds. At this instant, the ball reaches its maximum height of 10.1 meters. Okay, next, we will use the velocity equation to determine the time at which the ball reaches its maximum height. Since the velocity is 0 at this point, we will substitute 0 for v of t in the equation and solve for time. This gives us the time at which the ball reaches its maximum height as 1.02 seconds, which is consistent with our previous result. Now, we can substitute this time into the displacement equation to determine the maximum height reached by the ball. After solving the expression, we find that the maximum displacement matches our previous result, confirming that both methods yield the same solution. I'm sure you might be wondering whether we could use this motion equation to solve the problem. To clarify, it's important to understand the context of the displacement in this equation. Let's substitute the known values into the equation and see if the maximum distance aligns with the solution we obtained earlier. The ball reaches its maximum height when its velocity becomes zero. Since we already know the initial velocity and the gravitational acceleration, we can use these values to calculate the maximum height the ball attains. Wait a minute, why is this answer different from the one we obtained earlier? Which of the two is correct? This answer is correct if we measure the maximum displacement from the point where the ball was thrown. However, since the ball is launched from a height of 5 meters above the ground level, our reference plane, we must account for this initial height by adding it to the solution. This adjustment ensures that the maximum height is expressed relative to the reference plane, which is the correct approach. To avoid any oversight, we must make a slight adjustment to the previous equation by including the initial position, as shown in this updated expression. Here, S of t represents the displacement of the ball at any given time, while S sub 0 denotes the initial displacement from which the ball is thrown. Let me quickly walk you through the steps to derive this expression. Once we have that covered, we'll return to the question to determine the flight time of the ball. We can express time from the velocity equation as follows. Then, by substituting this expression into the displacement equation, we can solve for the square of the final velocity, v squared. We can use this motion equation for any situation, whether the ball is launched from a height or from the same level as the reference plane. Now let's return to the question and determine how long the ball remains in the air. The ball is launched from a height of 5 meters above the reference plane and completes its flight when it returns to the reference plane. This means that after falling back, its displacement relative to the reference plane is zero. We can substitute the initial position, initial velocity, and gravitational acceleration into the displacement equation to determine the flight time. Since this results in a quadratic equation in time, solving it will yield two possible values for time. We disregard the negative value, as it is not physically meaningful. Since the displacement equation follows a parabolic path, the trajectory intersects the time axis at 2 points. However, motion begins at time 0, and there is no movement before that. Therefore, only one valid time value remains, representing the total flight time of the ball, which is 2.46 seconds. Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video. Alright, now that we've got a good grip on vertical motion, let's dive into projectile motion. An object is launched from a flat surface with an initial velocity vector of 6 meters per second in the horizontal, I direction, and 8 meters per second in the vertical, J direction. Our first task is to determine the maximum height the object reaches and the time it takes to get there. Since motion in the horizontal and vertical directions is independent, we'll start by analyzing the vertical motion using kinematic equations. Next, we'll calculate the total flight time and use it to determine the total range. Just as in the previous section, we will use the displacement equation to determine both the maximum height the ball reaches and the time it takes to get there. The object is projected from the reference plane, so its initial displacement is 0. The initial velocity in the vertical direction is 8 meters per second, as given by the j component of the velocity vector. For simplicity, we will take gravitational acceleration as 10 meters per second squared. This is negative because measurements taken in the direction of the projectile's motion are considered positive. To determine the maximum displacement, we will rearrange the displacement equation as shown here. This will allow us to find both the maximum displacement and the time taken to reach it in a single step. The object reaches its maximum height when the expression inside the bracket equals 0. This corresponds to a time of 0.8 seconds. At this point, the maximum height attained is 3.2 meters. The maximum range is reached when the ball lands on the ground, meaning its height becomes 0 at that instant. Since vertical displacement follows a quadratic equation, there are two possible time values, one for the initial position and the other for the landing point. We will use the displacement equation to determine the time required to reach the maximum range by setting the vertical displacement to 0. As mentioned earlier, this results in two time values. We disregard the 0 value as it corresponds to the initial position and take the second value, which is 1.6 seconds. The velocity in the horizontal direction remains constant at 6 meters per second, since gravity acts only downward. Therefore, throughout the ball's trajectory, the horizontal velocity does not change. Given the total time of flight and the horizontal velocity, the range is found by multiplying these two values. This gives a range of 9.6 meters. I hope that explanation was clear. However, if you think otherwise, please mention it in the comments. Thank you. Now, let's move on to the next problem. A ball is thrown horizontally from the top of a 30-degree inclined plane. Given that the flight time is 3 seconds, we need to determine the distance the ball travels along the plane before landing. We do not know the horizontal velocity, but we do know that the vertical velocity is 0 at the starting point. Additionally, we can express the vertical descent of the ball in terms of the length L as L sine 30. To find the distance L, we apply the displacement equation in the downward direction. Remember, in this example, all measurements are taken in the downward direction, with the origin set at the point where the ball is thrown. Yes, the choice of the reference plane, direction, and origin is arbitrary and can be adjusted to simplify calculations, provided consistency is maintained throughout the problem. This flexibility helps in the easier application of kinematic equations and reduces computational complexity. The vertical displacement of the ball after 3 seconds is given by L sine 30. Both the initial displacement and initial vertical velocity are 0. Since all measurements are taken in the downward direction, gravity is considered positive. For simplicity, we assume gravitational acceleration to be 10 meters per second squared. The distance traveled along the slope is calculated to be 90 meters. Let's move on to the next question. An object is projected with an initial velocity described by vector coordinates, as shown in the diagram, where both k and m are positive scalar quantities. Point P lies on the object's trajectory and has a position vector xy, where x represents the horizontal displacement in the I direction and y represents the vertical displacement in the j direction. Our goal is to express y in terms of x and show that it matches the given equation. We assume the gravitational acceleration to be 10 meters per second squared. Using this, we will derive the equation for y in terms of x by eliminating time from the horizontal and vertical displacement equations. Let's start by expressing the vertical displacement y in terms of time t. The initial vertical displacement is 0, and the initial vertical velocity is given in the question. Since gravitational acceleration acts downward, we take it as minus 10 meters per second squared. Next, we follow a similar approach to express the displacement in the horizontal direction. The initial displacement is 0, and the initial horizontal velocity is provided in the question. Since there is no acceleration in this direction, the motion remains uniform. This gives us two equations in terms of time. From the second equation, we can express time in terms of constant k and x. Substituting this expression for time into the previous equation allows us to express y in terms of x. Okay, with that done, let's move on to the next part of the problem. Suppose k is equal to 1. Let's derive expressions for the maximum height h and the maximum range r in terms of m. Let's first rewrite the expression to visualize the maximum height. From this expression, we can determine that the maximum height h is given by m squared over 20. The maximum range occurs when the ball returns to the ground, meaning y equals 0. Substituting 0 for y, we can derive an expression for r in terms of m. Since the maximum range cannot be 0, it is equal to m divided by 5. Okay, now let's move on to part 3 of this problem. Point Q lies on the projectile's trajectory, where the velocity vector is orthogonal to the initial velocity. Our task is to determine the horizontal distance, x, to point Q in terms of m. Before determining the displacement x, we first need to find the velocity vector. This is done using our knowledge of vectors. We know that when two vectors are orthogonal, their dot product is 0. If we denote the velocity of the projectile at point Q as v, the dot product is given as follows. However, we have two unknowns, alpha and beta, which need to be determined. We know that the velocity in the horizontal direction does not change. Therefore, the value of alpha must be the same as the initial horizontal velocity, which is 1 divided by k. Now we are left with only one unknown, which is beta. To determine its value, we need to compute the dot product. Now that we have determined both alpha and beta, we can express the velocity vector v in terms of m and k. Since k is equal to 1, we can further simplify the expression. We have one more step to determine the horizontal displacement to point Q. By applying this velocity equation in the vertical direction, we can find the value of x. We will start by substituting the vertical velocity at point Q, along with the initial velocity in the same direction. We assume the gravitational acceleration to be 10 meters per second squared, just as we did earlier. We can substitute the expression we derived for any value of time. However, it is important to note that we have assumed k equals 1. Finally, after a few steps of simplification, we arrive at this expression for the displacement x in terms of m. I hope everything we discussed was clear. That wraps up this video. I hope you gained some new insights into projectile motion that you may not have encountered elsewhere. Hopefully, it was both informative and useful. If you haven't subscribed yet, please support the channel by hitting the subscribe button. Don't forget to like this video and share it with your friends. I'd love to hear your thoughts, so be sure to leave a comment below. Till we meet again in another video, take care and goodbye.